Wind is energy, a freely accessible and inexhaustible energy resource. Wind turbines can convert the wind to electricity. This was done by a test turbine in Askov in the southern part of Denmark already in 1891. When Denmark experienced an energy crisis in the 70s, the Danish environmental movement started the wind turbine production, which later turned out to be one of the biggest industrial successes in Denmark. In only a few years, wind power has become a realistic alternative to electricity produced by using fossil fuels. As the environmental consciousness has spread worldwide, there has been an increasing demand for wind turbines for sustainable, non-polluting energy production. 6 chapters of the story of modern wind turbines, a fairy tale of an industry and an energy emerging out of the blue. Since the beginning of time, the sun's rays have provided energy for the Earth. When the sun heats the Earth's surface, part of this energy is transformed into wind. The heating of the surface is different at the equator and at the poles. The wind speed and wind direction is determined by the difference in temperature and the rotation of the Earth. Denmark is situated in a windy area, but the wind conditions vary significantly from region to region. It is imperative for the output of the wind turbine that it is installed in a windy location. The fact is that twice the wind provides 8 times as much energy in the wind. Local conditions like hills, forests and buildings are also decisive for the production of a wind turbine. A good site along the coast yields twice as much energy as an inland site, and the taller the tower, the higher the production regardless of the site. All these conditions are described in the European Wind Atlas made by the Riso National Laboratory. The Wind Atlas provides a method to project the electricity production of a wind turbine. When the wind speed reaches 15 meters per second, 43 tons of air per second passes through the rotor of a 1000 kilowatts wind turbine. This is equal to the weight of 2 fully loaded trucks passing the rotor every second. Huge amounts of energy are thus converted to electricity in a wind turbine. The 3 blades attached to the hub is the rotor. The cabin on the top of the tower is called the nacelle. The hub is mounted on the main shaft. A yaw system with electrical motors can turn the nacelle on the tower. A gearbox connects the rotor shaft to the generator. An anemometer and a wind vane read the wind speed and direction, and the data is continuously analyzed by a computer which controls all the functions of the turbine. When the wind speed reaches 4 meters per second, the computer activates the yaw motor, which turns the nacelle and keeps the rotor turned into the wind. The wind is pressed against the blade, and the aerodynamic profile creates a high pressure on one side of the blade and a low pressure on the opposite side. The energy in the wind is hereby transferred to the blades, and the rotor starts to turn. The rotor is connected to the gearbox. The rotational speed is increased in the gearbox and passed on to the generator. When the generator has reached the speed where it can produce electricity, it is connected to the grid. The blades will then turn at a constant rotational speed. This is why the rotor of wind turbines of the same type and size are often turning synchronously. The turbine is built to deliver the maximum electricity production at a wind speed of 15 meters per second. When the wind exceeds 15 meters per second, some of the wind must be wasted to avoid an excess load on the turbine. Some wind turbine designs are controlled by turning the entire blade when the wind is too strong. This is called pitch control. Other turbine designs control the pressure on the blade profile by creating a zone of turbulent air at high wind speeds. This is called stall control. At gale force winds of 25 meters per second or more, the computer activates the hydraulic system, which turns the aerodynamic blade brake. Pitch control turbines use the hydraulics to turn the blade sideways. Stall control turbines turn the blade tips using springs. Then the disc brake is activated and stops the rotor. When the wind slows down, the computer starts the wind turbine again, and the electricity production continues. Today, this is a rare sight, but through the centuries, windmills were a common feature in the landscape. Wind farms were also known. This is a picture of Copenhagen in 1620. The test turbine from 1891 in Askov in the southwestern part of Denmark was one of the first turbines in the world to produce electricity. The turbine was made by the Danish Edison, Poul Lacour, who was a meteorologist and an inventor. Lacour educated electricians specialized in wind power, and this was a significant reason why the rural districts in Denmark had electricity before rural districts elsewhere in the world. In the 1950s, one of Lacour's students, the engineer Johannes Juel, developed the wind turbine design which is the predecessor to the modern Danish turbine, a three-bladed wind turbine with an alternating current generator. Political unrest in the Middle East resulted in an energy crisis in the 1970s. This inspired the energy and environmental movements to resume the Danish wind turbine production. The first wind turbines were manufactured in garages and sheds, and soon the local smiths joined in. But it was a carpenter, Christian Risager, who started a regular mass production of wind turbines. In 1978, students at the twin schools caught the world's attention by building the biggest wind turbine in the world so far, the twin turbine. Provocative evidence that producing electricity from megawatt turbines was possible. The turbine was built with voluntary assistance from Danish and international experts, and today it is the world's oldest operating megawatt turbine. To encourage the exploitation of renewable energy sources, the Danish government introduced a support system for installing type-approved wind turbines. This led to the creation of the Wind Energy Department at the Risø National Laboratory, which tests and grants type approval to wind turbine designs. The support system created a domestic market and prepared the ground for an actual wind turbine industry. A Californian support system for investments in wind turbines started an export boom for the young Danish wind turbine industry in the beginning of the 1980s. The Danish type approval requirement contributed significantly to the success, as it was considered a guarantee for the safety and production of the wind turbines. Since then, Danish wind turbines have had a world market share of 50%. Within 25 years, the Danish wind turbine industry has become the third largest export industry in Denmark with a multi-billion-dollar turnover. Denmark has 150,000 wind turbine owners, most of them members of a wind turbine cooperative. At the annual meetings held by the Danish Wind Turbine Owners Association, experiences are shared and the owners are informed of research and new developments. For more than 20 years, wind turbine owners have exchanged production experience and data in the magazine Natural Energy, published by the association. In this way, the wind turbine manufacturers have received the quick and valuable feedback to help improve turbine designs. The first mass-produced wind turbines were installed on lattice towers also used for overhead power lines. For aesthetic reasons, the Danish authorities now prefer tubular towers, so today all large wind turbines in Denmark have tubular towers. A turbine tower normally consists of two tower sections. How the tower surface is treated depends on the location of the wind turbine. There is a vast difference between desert sites, offshore sites, or a site in a Danish field. There is a wind pressure which corresponds to a weight of 20 tons at the top of a 50-meter tower. 1 meter above the ground, the force is 1,000 tons. This requires a strong and heavy foundation. When the electricity cables are buried, a phone cable to the wind turbine computer is also installed. The nacelle is assembled with parts from different component suppliers. This is a nacelle for a 1.65 megawatt turbine. The main shaft, gearbox and disc brake are assembled into one unit. The electronic controller and the electricity board for electrical power are produced especially for each wind turbine type. The unit, consisting of the main shaft, gearbox and disc brake, is mounted on sound-absorbing racks in the nacelle. The Risør National Laboratory is the world's largest research center in wind power. It researches aeroacoustics to minimize the noise from the wind turbines and in aero and structural dynamics to increase the efficiency of the turbines. As part of this research, strength and fatigue tests are carried out on new blade designs at the Risør test station in Sparkjær. Wind turbines continue to grow in size and new blade designs are constantly being developed. The blades are cast in glass fiber reinforced polyester or epoxy. Mats of glass fiber are laid in the cast and are encapsulated in polyester, which is distributed by a powerful vacuum. The blade is cast in two halves. A glass fiber beam is fastened to reinforce the blade and the two halves are glued together. The average blade length has increased from 5 meters to 30 to 40 meters in the last 15 years. The blades are checked for casting errors and are smoothened. To avoid reflections from the sun, the blades have a matte surface. Large wind turbines are difficult to transport. Blades and tower sections of 30 to 40 meters require special vehicles and good access conditions to the site. The hub is made of cast iron. This is the hub of a pitch-controlled wind turbine where the whole blade must be able to turn. The blades are fastened to the hub on the ground and are attached to the nacelle as one unit. Offshore turbines vary, especially in the construction of the foundation. These foundations for offshore use are made on land, for example, cast in reinforced concrete in a dry dock. The design helps to protect the foundation from ice. Transportation is not a big problem at offshore installations, but seabed conditions, currents, water depth and waves can create problems. Offshore turbines are especially protected from the salt and the tough conditions at sea, but the wind turbines are exposed to extreme loads in all kinds of weather and are often placed in remote areas with high repair and maintenance costs. Reliability is therefore an important competitive factor for the manufacturers, and intensive research is carried out to avoid breakdowns. In computer simulations, new turbine designs are exposed to extreme loads which are very difficult to create in real life. Several independent safety systems are installed in the wind turbines. All readings are sent to the controller, and if an error is discovered, the wind turbine is stopped immediately. The controller is connected to a telephone line, so all error reports can be checked around the clock, and all the functions of the turbine can be controlled no matter where it is located in the world. If there is a power failure and the controller fails, a mechanical safety system activates the blade brake and stops the turbine. The rotational speed is checked constantly, and sensors measure the temperature in gearbox, generator, and bearings. A drastic increase in temperature can be a sign of a defect. At an emergency stop, the blade brake and the disc brake are activated simultaneously, and the wind turbine is stopped within seconds. Wind turbines produce electricity as the wind blows, and even though more dependable wind forecast methods are developed, wind energy is still very hard to predict. In 1996, wind energy covered 4% of the Danish electricity consumption. Only 4 years later, the amount was 14%. Wind power is planned to cover half of the Danish electricity consumption by 2030. That much wind power requires new methods to control the grid. Wind turbine efficiency has improved remarkably within the last 20 years, as illustrated by the annual electricity production per square meter rotor area. The three-bladed turbine with an asynchronous generator has been the most popular design so far. But wind turbines with multipole generators or other types of wind turbines may possibly be developed to be more efficient and enter the mainstream market. No matter what the wind turbine design will be, everything indicates still larger and more efficient turbines. The number of Danish offshore wind farms will increase significantly in order to meet the goals to cover half the future electricity consumption with wind power. The difficult offshore working conditions will increase the installation costs as well as the maintenance costs because of the tough weather conditions. The advantage will be that the offshore turbines will produce more electricity because of the improved and more stable wind conditions, and the location many kilometers from shore will only have a minimal impact on the landscape. The first wind turbines were often very noisy, but since 1984, Danish environmental legislation has required that the sound level does not exceed 45 decibels at the nearest residence. This is equivalent to the faint noise of an office environment. Research in aeroacoustics is still being carried out to further reduce the noise from the wind on the blades. Rubber racks and other noise reduction precautions in the nacelles have reduced the mechanical noise from gears and generators. The sound from a modern wind turbine equals the sound of the wind in the trees at a light wind. At moderate winds, 8 meters per second, the background noise from the surroundings will block out the noise from the turbine. Possible noise problems from wind turbines will therefore most likely occur at very low wind speeds. Many wind turbines have been equipped with a second small generator, which sets in at low wind speeds. It produces electricity at a lower rotational speed and therefore reduces the noise level even further. Another irritation factor can be the light flashes when the blades cut the rays of the sun. The problem may occur to the east and the west of the turbine when the sun is low in the sky. Computer programs can calculate how many hours the surrounding houses can be exposed to this light phenomenon. Wind turbines are often mentioned as a risk to birds, and several international tests have been performed. The general conclusion is that birds are only seldom bothered by wind turbines. Birds quickly get used to new wind turbines and avoid the rotating blades. Studies show that, for example, overhead power lines are far more hazardous for birds. Human activity has always influenced the landscape. Modern society's demands for efficiency, mobility, and energy require large installations which inevitably have an impact on the landscape. But society's energy needs has a serious downside. Energy production exhausts the global energy resources. It pollutes the environment and can perhaps cause catastrophic environmental changes. Wind turbines produce energy without polluting, and therefore many governments in the world support the installation of wind turbines. Wind turbines continue to increase in size and can therefore be seen farther away, but the rotor of the large turbines also rotates slower and therefore causes less disturbance in the landscape. Are they beautiful or ugly? That is in the eye of the beholder. Maybe that is why wind turbines' influence on the landscape is one of the hottest subjects in the debate on wind turbine installations. Turbines must be installed very visibly in the landscape to yield the most efficient production. But one must really love wind turbines to enjoy such a sight. Many locations in the Danish landscape have a pressing need for wind turbine restructuring. The small, technically inferior wind turbines often block the good wind sites for the modern, far more efficient turbines. The total production from these 21 wind turbines installed in 1985 equaled the production of one 1,500 kilowatt turbine. Oil, natural gas and coal are limited energy resources and therefore not suitable for sustainable energy production. The electricity production from wind turbines in the year 2000 in Denmark alone saved the world resources from the incineration of 1.4 million tons of coal. This is equivalent to a coal train with 28,000 wagons in 1 year. At the same time, the environment was spared the pollution of large amounts of CO2, sulfur dioxide, nitric oxides, cinder, and fly ash. Researchers at the UN Climate Panel agree that pollution from the incineration of fossil fuels affects the global climate. They warn that measured over 1,000 years, the last 100 years have been the warmest ever, and the average temperature is still rising. A financial evaluation of wind power compared to electricity production from fossil fuels depends on the local wind conditions and varying political and market conditions. The situation is different if an environmental evaluation is performed. The manufacturing of wind turbines, of course, requires energy for steel production, tower production, blades, and nacelle. And energy is used for installation, maintenance, and scrapping. But on an average Danish site, the wind turbine will redeliver all the energy used in only 3 months. In its remaining lifetime, the turbine will produce 80 to 100 times as much energy as has been used for its manufacture, without polluting and without draining the global resources. From an ecological point of view, wind turbines are a very good deal. What started in the 1970s as a grassroots movement reaction to the energy crisis and nuclear protest has developed into the third largest export industry in Denmark with a multi-billion-dollar turnover and 15,000 employees. Intensive research, modern technology, and the effort of many committed and creative people have resulted in the development of an ecological and sustainable power plant that efficiently draws energy out of the blue.